So now that we talked about measures of center, and we talked about how there are two measures of center that are considered good, because you're looking at all the numbers in the data set. Now let's go on to talking about another type of measurement. So now we're going to talk about measures of variation. So just to motivate this, let's say that you have these two data sets. So each data set consists of three numbers. What is the measure of center of each data set? Or let's say the mean. What's the mean in both data sets? Yeah, it turns out to be 50. So if you just added these three numbers up and divide by 3, you'll see it's 50 in both cases. But just a shortcut to think about this is if you have the number, some number that is the same distance from its surrounding numbers, like this is a distance of 1, and this is a distance that's the same, 40. Then that number in the middle turns out to be the mean. So if you have a number that is in the middle, that is the same, that has numbers surrounding it that are the same distance around it, that balance it out, then that number in the middle turns out to be the same as the mean. So in this case, the mean is 50 in both cases. Okay, so the mean is the same. But just because the mean is the same for both set of numbers doesn't mean it's the same set of numbers. You see that these are very different set of numbers. So what makes them different is that you notice that the numbers on the left are packed much closer together than the numbers on the right. So the numbers on the right are spread much further apart than the numbers on the left. So we say that the numbers on the right has higher variation than the numbers on the left. So this has higher variation. And over here, left numbers has lower variation. But that's just looking at the numbers and being able to just get a feel for the fact that the right numbers has more variation. And more variation means that the numbers on the right are more spread out from each other as a whole. But that's kind of a very hand-wavy description. So how do you think we can quantify it more precisely? How do you think we can basically take each set of three numbers, basically put it into a formula that spits out an answer, that spits out a number, where that number will represent variation, and it's higher for the numbers on the right than it is for the numbers on the left. So how do we quantify the fact that the right set of numbers has higher variation? Yeah. Yes, but that's standard deviation is a very loaded, dense thing that we have to like unpack and work up towards. But in this simple example, how do you think we can, just using these three numbers, how do we conclude that the right set of numbers has more variation?
Calculate the distance between the center number and the outside ones.
Okay, great. So let's talk about that. So you notice, because variation is basically, we're trying to measure the overall spread of the numbers from each other, what we can do is we can find whatever the center is, and here the center happens to be the same as the mean in value. But instead of just trying to find the center number, or essentially the median, which may or may not be the mean, let's go ahead and just take the mean, which in this case is 50, and we're gonna find the distance of each of these numbers from the mean of 50. So we have this mean, and then we're gonna find the distance of each of these numbers from the mean. So the distance between 10 and the mean, we'll call that D1 for distance 1. And then the second one will be D2 for distance 2. The third one will be D3. So essentially, we're finding all the distances of each number from the mean, and then we're finding the average distance. And this is a very good way to find this measure of variation and quantify the variation. So essentially, we'll do that for both data sets. So let's go ahead and just look at this second data set here. And then let's go ahead and do what we just proposed, which is we're gonna find the average distance of each number from the mean. So take each number, subtract the mean, and that's the first distance, and we'll do the same thing for all the other numbers to find the other distances, and then we'll find the average distance. So the first distance we'll find is the first number minus the second number. But if we do that, are we gonna get a positive number or a negative number? Yeah, it will be a negative number, but that number is supposed to represent a distance. And you know that distances can only be positive. So this negative number, how do we ensure that it's positive?
Absolute
Yeah,
value.
we take the absolute value, very good. So in math, the absolute value is the operation that preserves the value, but changes the sign so that it becomes positive. In other words, we're finding the distance of this number from 0, and it's guaranteed to be positive. So this will be the first distance from the mean. What about the second distance? That'll be the 50 minus the mean, which ends up being 0. The absolute value of 0 is just 0. And then the third one will end up being
Blood groups of O, A, B, and on the randomly selected blood donors. Construct the relative.
so the third distance will be the third number minus the mean, and then we take the absolute value of that. And if it's already positive, we take the absolute value, then it'll continue to be positive. So that's the sum of all the distances from the mean, and then now we divide by the number of distances, which is 3. And then this is gonna give us the average distance of all the numbers from the mean. So it turns out that this is the ideal way to measure variation, to find the average distance of the mean by taking the absolute value at each step to make sure that the distances are positive. However, in real life, this is not what is done. And the reason for that has to do with math moving forward. So anybody in this class taking calculus yet? A few people, great. So for those of you who haven't taken calculus, I'll just explain this at a very a level that is big picture level. So in calculus, there's this operation called the derivative, where basically you spend almost the entire semester calculating the derivative of different things, different functions. And the derivative allows you to do something very important, which is to find quickly the maximum or minimum value that the function could possibly achieve. And so those of you who have taken calculus, if you take the derivative of the absolute value operation, is this messy or clean? You guys remember? Yeah, this turns out to be a very messy operation. And the reason for that is the absolute value, if you were to graph it, has this sharp point here. And the derivative is not defined at this point. So now you have to break it up into separate cases to find the derivative. And so this operation is very messy. So later on, we don't want to encounter something this messy. So we don't want to define an operation at this point where we're going to introduce problems later. So even though this absolute value is ideal, we don't want to introduce it into this new calculation for variation. So let's back up then. Instead of the absolute value, to try to make the number positive, what else do you think we could do? We might be changing the value, but still making it positive to represent a positive distance.
Square it?
Yeah, very good. We could square it instead, and when we square it, that might change the value of the number, but at least it's still positive to represent a positive distance. So we're going to square all of these instead. So it turns out that this is a measure of variation that people use in real life. So this measure of variation is called the variance. And the variance is basically not the average distance from the mean anymore, but now it's the average square distance. So the variance represents the average square distance from the mean. But remember, we had to square this to kind of try to duct tape this situation where we didn't want to use absolute value, so we're squaring instead to make sure that the distances are positive. But we end up with this concept that we didn't quite want from the beginning. From the beginning, we wanted the average distance from the mean, not the average square distance. So what do we do to try to partially undo this?
Square root?
Yeah, we're going to take the square root of this whole thing. So the square root of this whole thing we call that the standard deviation. So this whole thing, including the divided by 3, we're going to take the square root of that whole thing. And this is the standard deviation. The standard deviation is equal to the square root of what we did before, which is the square root of the variance. Which is the square root of the average square distance from the mean. But the question is, if we took the square root of the average square distance, we now get exactly what we wanted, which is the average distance from the mean. So does this equal the average distance from the mean? If we take the square root of the average square distance from the mean, does that equal the average distance from the mean? Any guesses? So let's just look at some simpler numbers. So let's say that this, represents an expression that represents the average square distance from the mean. And, oh, sorry. So let's say this represents the average square distance from the mean. If you take the square root of the whole thing, does this square root undo each of the squarings so that this becomes just this? So originally, we wanted this, but we were forced to square each thing. But now if you take the square root, are you gonna undo each of these individual squares? It turns out that you undo it only partially. You don't do it exactly. So if you actually evaluate these numbers, on the left here, you're gonna get 1 squared, which is 1, plus 2 squared, which is 4, plus 3 squared, which is 9. So 1 plus 4 plus 9 is gonna give you 14. So you're gonna get the square root of 14. And square root of 14, does that equal 1 plus 2 plus 3? Yeah, that doesn't equal that, because 1 plus 2 plus 3 is gonna equal 6. So if you're starting out with squaring each thing, and you take the square root, it's not gonna undo each of these squares exactly. You're gonna undo it partially. So that's why when you take the square root of this average square distance, you're not gonna get exactly the square distance from the mean. You're gonna get approximately the square distance you're gonna get approximately the average distance from the mean. So that's why we're gonna do this, approximately the average distance from the mean. Any questions? Okay, so that's what the standard deviation is. So again, you can think of the standard deviation as being the average distance of each number from the mean, but approximately. And maybe this whole approximately business bothers you, and it should. And the reason why this approximation is not that big of a deal is because usually we only use standard deviation in comparison. So we're comparing the standard deviation of one data set with the standard deviation of another data set. And if both of them are approximately the average distance from the mean, then the relative comparison is all that really matters. And if one standard deviation is bigger than the other, then we say that it has more spread in its numbers than the other. Okay. Any questions?